Yes, dear students, we are going to complete the different cases of Doppler effects. There are some cases left, and one of them is, so when observer and source are not in the moving not in the same directions. Our source is moving in these directions, and the line of action of our observer is in different directions. Earlier case, we have directly the motion of the observer and source are in the line joining of them, but in that case there is motion in a different way, moving in different line. So we have to take the component for calculating the apparent frequency of the moving sources. We have to take the component of velocities along the line joining of observer and sources. Our velocity along this direction is VO V naught, and along this will be VO cos theta V naught cos theta, and our source is moving along this direction. So therefore the velocity of source along the line joining of observer and source will be Vs cos theta Vs cos theta. So in this way we can use earlier cases, formula of the earlier cases. So here observer is moving toward the source and source is moving away from the observer. Therefore the frequency, there will be the effect of both the cases. Now first case, the observer is moving toward the sources. We have taken consider only the component, only the velocity component of the V naught along these ones, and we already know that velocity V is the velocity of the sound in air. Therefore sound velocity, sound produced by the sources moving in all directions, and one way to represent it along these ones, our source velocity is along these ones, the sound which produced by the source is moving along this one also. So now this is the direction of the velocity of the source which is heard by the observer. Now we velocity of sound in air and V naught is the observer velocity, and Vs is the source velocity which is moving toward this one. So we have to consider both the cases simultaneously. One is observer reducing the distance between observer and sources move away from the observer. Therefore the simultaneous effect on the apparent frequency will be, therefore this is fa is the apparent frequency, and also f naught is original sound frequency. This is our original sound frequency. Yes, now the apparent frequency in that case will be is equal to since the frequencies it is appear to increase by the observer because observer is moving toward the sources. Therefore velocity of sound in air plus velocity of observers along the line joining of observer and source, which is V naught cos theta divided by velocity in air, and this is a plus because source is moving away. It will reduce this factors of f naught. Therefore we have to increase the denominator. Therefore Vs cos theta, V plus Vs cos theta. So this is the resultant effect of the moving sources and our moving observers when they are not in the moving in the same line joining. So let us do one numericals under this observations. Yes, this is one problem which is based on the when sources, our source and observer are moving it in not in the same joining of the straight lines. So here, suppose this is our car. Car is moving along this one. The car is sounds some sources. The car, yes, the car sounds some horn, and the observer is our observer is at rest. It is not moving. In this case, the velocity of the observer is 0, and our car is which uh, sounds a horn moving along these directions. This is the velocity of source, which is already given. So velocity of source, which is 20 meter per second. 20 meter per second velocity of the sources who's moving along CS, and our observer is at rest. It's not moving this ones, but the car is not moving along the joining of this source and this observers. The car is moving along this one, making some angle theta. Suppose it makes an angle theta along this one. We need to calculate the apparent frequency which is heard by the observer, which is at some angles theta from the straight line this, and that angles if it is given that it is not given, so we have to calculate by this geometry, because this distance 80 meters, 60 meter and 100 meter we can calculate easily from here. Now we need to find the component of source velocity along this one, which will be Vs cos theta. Vs is along this one, Vs cos theta will be along this one. We need this one. Vs cos theta is the component which is moving toward the observer, therefore our apparent frequency will increase. Now our answer will be apparent frequency which is heard by the observer frequency of the original frequency of the sources, which is 5 hertz, 500 hertz. This is 500 hertz, and we have 500 hertz, and therefore the formula becomes f original frequency multiplied speed of the sound in air, which is 330 meter per second. It is given here 330 meter per second, and source velocity is already mentioned, which is 20 meter per second. This is the source velocity, 20 meter per second. If I put all these values here, original frequency multiplied V divided by, since the component of the source is, I can say that the source is moving toward the observer, therefore the denominator should be smaller than that of the numerator, so that the factor of f should be greater than 1. Therefore V minus Vs, always the velocity of the sources, if there is any changes in the frequency, if the apparent frequency is changing, so source component comes in the denominators, and due to the, if the observer is moving, due to which if the apparent frequency, if the frequency is changing, and then the component of the observer should always remains in the numerator. If I put all the values here, I will get frequency, original frequency 500 hertz, and the frequency of sound in air 330 meter per second. 330 divided by 330 minus Vs, source velocity 20 meter per second, and cos theta should be calculated from here. If I find the value of cos theta from these triangles, cos theta is equal to base into altitudes. This is your theta, and it will be your base, and it is your perpendicular, it will be your hypotenuse. Therefore cos theta will be here base, which is 80, cos theta base divided by hypotenuse, S for hypotenuse and V for base. Therefore our base will be 80, and hypotenuse here, this is the hypotenuse, its length is 100 meter. If you cancel 0, it comes out 8 upon 10, If I put the value 8 upon 10 is here, 8 upon 10. After simplification, these values are found 500 into 330 divided by 330 minus 2 into 8, 2 into 8, it will be 16. After some simple calculations, this value will be 330 minus 16 will be 314, and now if I multiply it and calculate it, this value comes out 525.5 hertz. 525.5 hertz is our answer. You look here, our original frequency is 500 and our apparent frequency which appear to the observer is 525.5 hertz. So it means that the apparent frequency is more than that of the original frequency. So in this way, by using simple calculations and the concept, we can easily find the apparent frequency which is heard by this observer. That's all. Thank you very much.